Now, there were several studies that were carried out with different materials and approaches. However, there's this approach I'm going to focus on, which was nanostructured ceramic coatings. It was developed at the University of Connecticut by Maury Gill and his associates. The general approach is to take nanoparticles, agglomerated to micron-sized particles that are typically used for thermal spray. You introduce that to your thermal spray torch, apply the coating, and this is a real simplified schematic view of the two most important features. The fully molten particles quench upon impact and form this dense matrix. And incorporated in that matrix are these unmelted particles, which you cannot avoid. In thermal spray, you're always going to have unmelted particles because you have a size distribution of particle size, and when you introduce it to your hot zone, here, the jet or the flame, not all of it sees the same thermal history, and so you're going to have some particles that don't melt fully. So they retain a lot of your original feedstock features. When you take a close view of these unmelted particles in these coatings, you can see that they are agglomerates of very fine particles. And initially within the program, everyone was saying, hey, let's try to avoid having these loosely bonded agglomerates because they may be weak sites where it just crumbles. However, in hindsight now, if we were to eliminate these unmelted particles, we in fact would not have any difference compared to conventional materials. The presence of these unmelts are critical to what we're going to see in a moment. So this is what we coined as the flagship result. This is the best result within the program. And it revolves around the alumina titania ceramic, which is you can get in commercial powder form from Medco, Sulfur Medco. And these are samples after they underwent 2 tests. One side of these steel plates were coated with conventional alumina titania and then the nano alumina titania. And on the top, these are remnants after holding the samples along the perimeter and pressing the backside, the side that's not coated, against the ball bearing, and pressing it with enough force that you actually deform the substrate. So they call it a cup test. So form a cup shape. You can see the conventional ceramics being brittle. It just kind of cracks, just falls off. You can see the nano coating actually took the shape of the cup and stays on. They then took the same samples and bent these samples around a half-inch rod at 180 degrees. All the coating was removed, so they didn't bother showing you that sample. Here you see there's a little bit of coating removal at the edges. However, majority of coating was retained on the surface. So the advantages that they saw have double the bond strength, at 4 times wear resistance against 3-body abrasives, abrasive wear testing, had remarkable toughness and was qualified under the standard 1687A. Typically, to get a new material or process onto a Navy craft, the qualification time is quite long. I don't think it's quite as long as for spacecrafts, but it still can extend to about 10 years before you receive qualification. They want extensive testing to make sure you don't have failure during service. However, in this case, due to the promising results, they accelerated that process at the Naval Surface Warfare Center in Carter. They did extensive testing, fairly quick pace, and then a gentleman by the name of Ken Scandell pushed this onto a Navy application. Here's some examples. This is the USS Enterprise. I think this is the first nuclear aircraft carrier. And these are just examples of some of the components where these coatings have been applied. And they're mostly simple shapes, for rods, cylinders, easy to apply in those geometries. But there's one application that really stands out, and it revolves around this. These are minesweepers, otherwise known as mine countermeasures, CMCs. So they play a real critical role, obviously, in the fleet. And the component that we're going to focus on, I don't know if it's very visible, but They are two propeller shafts. I don't think
There's a big the other line to it.
Yeah. Okay, here you see, this is the propeller here, and you can see the shadow of the other one here. There's two of them. And the shafts were undergoing extensive wear. And due to the reasons relating to these ships, a lot of the new mines can be triggered by magnetic field. And because of that, the Navy does not use steel shafts. They use hollow nickel, aluminum, bronze shafts. Nickel, aluminum, bronze is relatively solid. This is a long, hollow cylinder. So by being soft material, it's prone to wear. And the wear occurs at the bearing regions. And the main source for the wear is the fact that you have these biogrowths, calcareous buildup from exposure to seawater. And the problem doesn't arise while the propeller is rotating. It arises during startup, because when you have stop and you try to start up, you have direct contact between the bearing surface and the shaft surface, and then you have these abrasives that form in between, so it starts scoring your shaft. And in some cases, they've actually lost the propeller. Scored so much, it just fractured, and lose the propeller. But once it gets rotated, it's designed to form a water bearing, so you don't have contact with the rigid surface. So it's really startup that's the main issue. So the issue is, why would you put a ceramic coating on here where on stop startup you're going to have a lot of torquing, you're going to have a lot of movement. Ceramics is the last material you would put on, right? Because it's brittle. However, based on the results that we saw, it looked like it was pretty tough and that it would sustain the strain that it's exposed to. So they went ahead and did that. Just want to show you here, this is the type of wear level you can see in these shafts after about 18 months in service. So the old method of repair was to send it back to the original equipment manufacturer. They would well repair the four bearing regions. This is the two ship set. And then they would machine it down to the original tolerances. That came at a cost of $280,000 for the ship set. And it typically needed reworking after about 18 months. Because of the heat-affected zone produced while you're welding, you can't repair this indefinitely. After a certain number of times, it's just too brittle, you can't weld repair it again. The new approach was to use air plasma spray, and here you can see them spraying onto the shaft itself the nano aluminum titanium coating. And this work was carried out at Norfolk Naval Shipyard. You can see they're grinding down the coated region to original size. And that came at a cost of $75,000 for a ship set. Now, in February of last year, the Navy asked Perpetual Technologies and F.W. Gardner to go and take a look at and do a non-destructive analysis of the coatings. I believe they dry docked in San Diego and sent the shafts to Norfolk. And we went in and we were really excited because prior to this, they sent an underwater diver to look at it when they brought one of the ships to Galveston. And you know, you're underwater and you're taking these photos. The coating looked good, but you know, we weren't absolutely sure what the integrity and whether or not there was some spallation in little areas. This was the first time we could really take a close look at these shafts. Now the shafts came from the ones that we looked at.